A primary occupation of the field of causal inference is the estimation of causal effects. But what exactly do we mean by a causal effect? We'll set forth these fundamental notions in this video. Suppose that I have a headache and decide to take an aspirin to help it pass. An hour later, my headache is gone. Did the aspirin cause my headache to go away? Well, it depends. What would have happened if I had not taken the aspirin? If, without the aspirin, my headache would have stayed, then we would say that the aspirin caused my headache to go away. There was a causal effect of the aspirin. But maybe, without the aspirin, my headache would have gone away naturally. In that case, I would not say that the aspirin caused my headache to go away. There is no causal effect of the aspirin. We can make this intuition more precise from a statistical standpoint by defining some notation. Let A be a binary valued random variable that equals 1 if the treatment, aspirin, is taken, and 0 if the treatment is not taken. The headache outcomes that could potentially result in either of these situations are called potential outcomes. We'll indicate 1 for headache and 0 for no headache. We can denote the 1 hour headache outcome, where I took aspirin, as Y with a superscript A equal to 1. This is referred to as the potential outcome under treatment. In this situation, this potential outcome equals 0 because my headache went away. We can denote the 1 hour headache outcome where I didn't take aspirin as Y with a superscript A equal to 0. This is referred to as the potential outcome under no treatment. Suppose that my headache would have persisted without the aspirin. Then this potential outcome is equal to 1. Because in this situation I actually took aspirin, the potential outcome under treatment is the one that is actually observed in reality. The potential outcome under no treatment is not observed in real life because A equals 0 did not actually happen. This potential outcome that is not observed is also often referred to as the counterfactual outcome because it's the outcome that would have resulted if I had foregone the treatment, counter to the fact that I actually did take aspirin. So with this notation, we can statistically define causal effects. We say that there is no individual causal effect if the potential outcomes under treatment and no treatment are identical for a person I. In this situation, we say that the null hypothesis of no individual causal effect is true. An individual causal effect exists if these potential outcomes are different for that person, and this effect can be quantified in different ways, such as a difference or a ratio. The problem with trying to estimate individual causal effects is that only one of the two potential outcomes is ever observed in real life. Generally, individual causal effects are not within our reach, unless we're willing to make substantial assumptions. But this isn't to say that causal inference is hopeless. Let's consider another type of causal effect, an average causal effect. Average causal effects are more attainable statistically and generally more of interest from practical policy standpoints. Let's say that we have data on an entire population of individuals. Each of these individuals has two potential outcomes shown in this table. With information on both potential outcomes, we could compute individual causal effects for each person, but we'll focus on the average in each of the two columns to define the average causal effect. We can look at the average of the potential outcomes under treatment. Because this is an average in the entire population, this average is the expected value of the Y equal 1 random variable. Note that because the outcome is a binary, Bernoulli random variable, the expected value is also equal to the probability that it equals 1. Here, the probability of a headache if everyone were to take aspirin is 1/6. We can similarly look at the average of the potential outcomes under no treatment. The probability of a headache if everyone were to not take aspirin is 4/6. An average causal effect, ACE, in the population is present if the two expected values are different. If the two expected values are the same, then the null hypothesis of no average causal effect is true. In this case, the two expected values are different, 1/6 and 4/6, and we would say that there is an average causal effect. There are many different ways to define the average causal effect, a difference or a ratio in the mean potential outcomes. If the outcome is binary, the causal effect can also be expressed as an odds ratio. Because the ACE describes comparisons of average outcomes, It is generally more of interest to policymakers than individual causal effects because policies and programs necessarily impact many people. And the key desire for policies is to allow for improved outcomes overall. Note that what we've done is to use a complete set of information on all potential outcomes in order to clearly define the average causal effect. Let's consider what things look like in reality where we don't have this full information. In reality, we would only observe data that look like this. The first half of the population took aspirin, so we would only observe the potential outcomes under treatment. The second half of the population did not take aspirin, so we would only observe the potential outcomes under no treatment. This missing data on potential outcomes seems like it would prevent us from being able to estimate average causal effects. What might help us move forward? What if we could conduct a study or analyze data in such a way that we could essentially fill in the missing potential outcomes? As we move through this course, we'll make these ideas more precise and develop statistical tools and ways of collecting data that will enable us to estimate average causal effects that are so important in understanding and improving our world.